Evening, participants. So today, as part of your advanced materials chemistry course in the subsection of functional materials, we will be covering the remaining part on magnetic materials. If you remember, in the last class, we had spoken about different fundamental concepts of magnetism. And today what we are going to do is we are going to see what are the different devices which are possible using the magnetic materials. So today in the class, we will cover application of magnetic materials, which will cover both hard and soft magnetic materials. Then we'll talk a little bit about giant magnetoresistance materials and their various applications. Then we'll discuss the concept of ferroelectrics. Then we'll talk a definitive application of ferroelectrics, which is ferroelectric RAM. Then we'll talk about a particular effect which is known as magnetoelectric effect. And we'll talk about multiferroic materials and their various applications. So this will cover our entire magnetic materials portion. So if you remember in the last class, we had spoken about hysteresis, we had spoken about M versus H curves, and then we had spoken about how when you have a hysteresis loop, so when there is a loss, as you can see over here, some energy loss as it is cycling, as you are increasing the H field, as you can see over here, then what you find is basically there is some kind of a remnants and then there is a coercive field. So if this coercive field is very strong or very large, then we say that what we have is a hard magnetic material. And oppositely, if you have a coercive field which is relatively much less, in that case, you have a smaller loop area, a smaller coercive force, and we say what we have is a soft magnetic material. So there are distinct applications of hard magnetic materials as well as that of soft magnetic materials, and this is what we are going to discuss. So among the hard magnetic materials, these are mostly the ones which we say as, which forms permanent magnets. So what you have in this case is you have a particular magnet, and for the first time when you're exposing it to an external magnetic field, then by the domain wall motion and the domain wall rotation, what happens is that entire magnetization or the magnetic moments, they get aligned to the external magnetic field. And when you remove the magnetic field, it stays in that form. So it forms a kind of permanent magnet. So what are the different materials which you can classify as hard magnetic materials? Of course, you have steel, you have various ferrites, then you have alnico, which is aluminium, nickel, and cobalt, combination of that. Then you have those rare earth incorporated magnet materials. So here you have samarium and cobalt. And then you have neodymium, iron, and boron mixed together. And those are different combinations of hard magnetic materials. So what we are looking over here is, if you look into this graph, we are having the maximum energy product, that is VH over here, and we are having the year of development. So if you look, as gradually when we started in 1900, 1920 or so, it was steel, and currently what we are looking at is at 2010 and 2020, it is basically the NdFeB kind of materials. So what is the need for this enlarged energy densities? So the main motive is the development of rare earth permanent magnets. And most importantly, this comprises of less dysprosium containing Nd2Fe4B type magnets with much improved temperature stability for electromotor applications at the higher temperatures. 450 K is much higher than your room temperature. So that is the reason why we are looking into enlarged energy densities for these different magnetic materials. So these hard magnetic materials, they have a very wide range of applications. So in automotive industry, they are used as motor drives for fans, wipers, injection pumps, starter motors, control for seats, windows. In telecommunication, you have microphones, loudspeakers, telephone ringers. They all have some permanent magnets attached to it. And in data processing, you have printers, stepping motors, disk drives, actuators. In consumer electronics, it is used in home computers, in clocks, in DC motors, for the showers, etc. Then you also have electronics and instrumentation field, where you find these kind of hard permanent magnetic materials in energy meter discs as sensors, as dampers. And in industrial application, of course, lifting apparatus, robotics, meters, in astro and aerospace, in auto compass, couplings, instrumentation, and in biosurgical for NMR, MRI, body scanners. For all this, you require different kinds of magnets. And presently, what we are looking at is basically rare earth-based magnets. But more and more, we are looking towards less dysprosium incorporated rare earth magnets because of the very high energy density that these kind of magnets can have. Then in soft magnetic materials, they have very, they are very, very important for power electrical applications, such as in generators, in distribution transformers, and a broad assortment of motors as well as electronics, where you require mass of inductive components. So wherever that induction-based magnetization is required, then you want to look into soft magnetic materials. So here you can find in this particular graph basically the saturated magnetic flux density, which is given in the x-axis, and this is plotted against permeability, as you can see. For soft magnetic material, the permeability has to be much appreciable, at much higher. And when you're looking into miniaturization, then basically the saturated magnetic flux density also has to be higher. So different groups of materials, they fall in, in different areas in this particular plot. So you have various cobalt-based amorphous alloys, as you can see over here. Then you have permalloys. Then you have iron-based amorphous alloys. You have silicon steels, and you have iron. So iron, as you can see, the saturated magnetic flux density is very high. But if you look into here, the permeability is very low. So iron is mostly a hard magnetic material. Whereas if the saturated magnetic flux density is not, is a bit low, but the permeability is very high. So these are basically very good soft magnetic materials. And somewhere in between, you have between the hard and the soft, which has medium kind of saturated magnetic flux density and also appreciable permeability. Those are basically the cusp area where it is lying between hard and soft magnetic materials. So soft magnetic materials, they can have direct current applications. So direct current, as you know, is basically current which is in particular, you are applying in one particular direction. So the material is magnetized in this particular case to carry out an operation, and then it is demagnetized at the last part of the operation. So for material selection, when you are looking into DC application, the main consideration is going to be permeability. High permeability will be required if you want a DC application. And this is generally used in the field of magnetic shielding, in electromagnetic pole pieces, and to activate the solenoid switch. Permanent magnet uses this material to make a path for flux lines. So these are the different applications, DC applications of soft magnetic materials. Whereas when you look into the alternating current applications, that's AC ones, then the material will always be in magnetized state throughout the time of the operation. So when you are having an AC application, the material always stays in a magnetized state. Whereas in case of DC application, you saw that when you are carrying out the operation, it is magnetized and it has to be demagnetized during the last part of the operation. So when you are having an AC application, the main criteria for material selection is going to be the amount of energy loss in the system. As you know that whenever the material, that MH curve, when that hysteresis loop is occurring, what essentially is happening is there is an energy loss. So whenever you are looking into a good material for AC application, you have to see that this loss is minimal. So obviously the coercivity has to be less, and in that case you need to look into some material where the HC value is very, very low. So this is generally used in power supply transformer, in DC-DC converter, in electric motors. And normally the greatest application or the maximum application of this soft magnetic materials is in the field of this power supply transformer. So all our transformer lines basically has this kind of soft magnetic materials. So now we look into this particular slide is showing you the different applications of functional magnetic nanoparticles. So when we are looking into research in magnetic nanoparticles, what are the different areas and the different types of magnetic materials you can work on? So suppose you have a magnetic nanoparticle. Mostly when we talk about magnetic nanoparticle, we have something which is either Fe3O4, or we talk about something which is Fe2O3. There can be other materials also, But let's consider these two examples. You have either Fe3O4 or you have Fe2O3. So if we are looking into it, then what we have in this case is that you have this particular magnetic nanoparticle. So on this magnetic nanoparticle, if you are putting in some dyes, if it is absorbing these dyes, then this magnetic nanoparticle can be used for something which is known as multimodal imaging. So for imaging purposes, you can use these kind of magnetic nanoparticles on which dyes has been put. The other thing is you can have different kinds of ligands or receptors which are attached to this magnetic nanoparticle, and you can use it again for detection purposes. So these are bacteria detection, protein separation. So for all these kind of applications, you can have a magnetic nanoparticle in which you can actually have some ligands or receptors attached. So on the magnetic nanoparticle, you will have some functional groups. On that functional groups, you will put in these kind of ligands and receptors. And once this nanoparticle is ready, then you can use it for the detection of bacteria, for protein separation, and all such different activities. Otherwise, what you can do is on the magnetic nanoparticles, you can put in antibodies or DNAs. And so you have something which is like this biomolecule, as you can show here, as it is shown over here, you have this magnetic nanoparticle on which this biomolecule is attached. And then you can use it for specific binding, drug delivery. So on these antibodies and or the DNAs, what you have is you have this kind of, so all these antibodies and all, they are kind of the drugs which are there, and you can have it for drug delivery kind of applications. Then as such, the magnetic nanoparticles, whatever you have, you can form quantum dots. So these are nano components. And again, you can use it for multimodal imaging. You can have nanoparticles, this entire thing as nano drugs. And this is again for drug delivery as well as for MRI applications. And you can have these different metal nanoparticles, metal magnetic nanoparticles, which can again be used for multimodal imaging as well as for their multi-balancing. These kind of applications are there for functional magnetic nanoparticles. So now we come to the next topic, which is your magnetoresistance. Magnetoresistance, as I had discussed in the last class, it is basically the dependence of electrical resistance of a sample on the strength of the external magnetic field. So what you have over here is this delta H is equal to your RH minus R0 by R0. So RH is nothing but the resistance of your sample in the magnetic field H, in the presence of magnetic field H, whereas R0 corresponds to when you are not having any external magnetic field applied. So what is giant magnetoresistance? If you remember today I told you that today we'll discuss giant magnetoresistance. Magnetoresistance concept I had already discussed in the last class. You can check the slides and you can see. So today what we are going to talk about is something which is known as giant magnetoresistance. So this indicates that the value of this delta H, what you see for multilayer structures, significantly exceeds the anisotropic magnetoresistance, which is generally has a value within typically between a few percent. It varies with a few percent. So that is normally materials, they have an anisotropic magnetoresistance. Okay. But in this case, what we are talking is we are having some multi-layer structure, and due to the fabrication of this multi-layer structure, what you actually impart into the material is very high magnetoresistance, and that can have multifarious application in various kinds of devices, which we will see later. So this giant magnetoresistance effect, this was discovered by Grunberg and Ferd, and that was in 1988. So this is basically nothing, as I said, is a large change in electrical resistance, which is induced by the application of a magnetic field to thin films composed of alternating ferromagnetic and non-magnetic layers. So as I said, you have a layered structure. So in that layered structure, in one layer, you have a ferromagnet, which is followed by a non-magnetic layer. Again, you have a ferromagnetic layer, and then you again have a non-magnetic layer, and so on it goes. So this change in resistance is, in general, what the change in resistance is nothing but a reduction. This is related to field-induced alignment of the magnetization of the magnetic layer. So when you're applying the field, the magnetization in this magnetic layers, they become aligned, and this causes a change in the resistance. So when in the first experiment, which was done in 1988, the films, they were composed of layers of ferromagnetic iron and non-magnetic bromine. and the typical thickness was around a few nanometers, and the current which was applied was in the plane of that particular film which was made. But please note that this magnetoresistance effect, it can also be obtained when you are having a current which is applied perpendicular to the layer, to the plane of the layer. So what is the origin of this giant magnetoresistance? It is the dependence of the electrical conductivity of the ferromagnetic materials on the spin state of the carriers, and the carriers in these cases are nothing but electrons. So it is dependence of your electrical conductivity of your ferromagnetic material on the spin state of the carriers it is having. So you have a change in electric conductivity in a system of metallic layers when an external magnetic field changes the magnetization of the ferromagnetic layers relative to each other. So whatever I said over here is given pictorially over in the diagram, as you can see over here in this picture. So in one case, when you're applying, what you find is the magnetization is pointing, the M1 and M2 are in the same direction, whereas in the other case, you find it is opposing each other. So the effect is generally described by delta R by R. So R parallel and R anti-parallel, they are resistivities for this parallel and anti-parallel alignment of your magnetization. Alternatively, sometimes this ratio, here we have given R parallel, but you can also define is an R anti-parallel. And this effect, it originates from the spin-dependent transport of electrons in the magnetic material. So what I exactly mean by this spin-dependent transport, this is what I am going to discuss. So now the charm of this system, it lies in the fact that it enables sensing of the external magnetic field strength in electrical units in between the two electric states of resistance. So what it does is you have two electric states of resistance, and giant magnetoresistance, it will give you a way or a method of sensing the external magnetic field strength. But this external magnetic field strength will be discussed in electrical units. And this GMR technology finds a lot of application in air and space and automotive industry, in non-destructive material testing. Compass functionality in your mobile phone, you have that compass functionality. That is basically due to a GMR effect. A GMR type of material is there in your mobile phone, which enables you with this compass functionality in the mobile phones. Several biomedical techniques uses GMR, like biometric measurements of eyes and biosensors for the detection of viruses. So for all these things, what you need is GMR materials. So as I said, it's a change in the resistance of the magnetic multilayer as a function of the applied magnetic field. So suppose I have this magnetic field over here at 0. In this particular case, in these two layers, the two layers of the ferromagnetic material, the magnetization is opposing each other. And here you have a 0 magnetization. Now, as and when you start applying a magnetic field, the moment the magnetic field, exceeds the saturation field HS, what you have is a structure like this, where in both the ferromagnetic layers, the magnetization is pointing on the same side. So they are parallelly aligned. So at the starting point, it was anti-parallelly aligned. When you apply a magnetic field, then this particular thing, it becomes parallelly aligned. Then if you go to the negative direction, so you are applying a field in the other direction, then exactly the opposite thing happens. So this is basically the magnetization curve for the multilayer. And this is what is showing you the resistance, how the resistance changes. So when it is basically when your no magnetic field is getting applied, in that case, it has the highest resistance. It is anti-parallel to each other. But the moment you start giving the field, the resistance decreases. So as you increase the field on one side, the resistance decreases. If you apply the field on the other direction, then also the resistance decreases. So here what you have is the resistance change, which is happening due to the application of the field. So now, what is the origin? So this is something very interesting. Now the electrical conductivity in metals, it can be described in terms of two largely independent conducting channels corresponding to the upspin and the downspin of electrons. which are distinguished according to the projection of their spins along the quantization axis. So what exactly it means? That in your metals, what you have is upspin electrons and downspin electrons. And these basically provide independent conducting channels. So when you talk about electrical conductivity in a metal, it is basically a resultant of these two largely independent conducting channels. So one is due to the upspin electron, the other is due to the downspin electrons. And this is generally given by the projection of their spins along the quantization axis. So this upspin and the downspin, you have to remember, they don't mix over a long distances. And therefore, the electric conduction occurs in parallel for the two spin channels. So if you see this entire, the total value is nothing, but this electrical conductivity is a summation of the conduction of the upspin electrons and the downspin electrons. And they are not mixing with each other. For a very long order, for a very long distance, these two channels stay separate. But you have to remember one thing, that when we talk about the band structure of a ferromagnet, it is exchange split. So if it is exchange split, that means the density of states is not the same for upspin and the downspin electrons when it is having the Fermi energy level. At the Fermi energy level, so the DOS is very different for an upspin compared to that in the downspin. So now the scattering rate or the resistance, we say the conductivity or the resistance, however you want to express it, this is proportional now to the DOS, that is the density of state. So the resistivities are going to be different for electrons of different spin, because the density of state, as I mentioned in the previous paragraph, that it is different when you are having a band structure in a ferromagnet, because it is exchange split. So the DOS is different for upspin and downspin. So automatically the resistance is going to be different for the upspin and the downspin channels. So now it is assumed, this is an assumption, that the scattering is strong for electrons where the spin is anti-parallel to the magnetization direction. And it is weak for electrons with spin which is parallel to the magnetization direction. So now, this reflects what the asymmetry in the density of state at the Fermi level in accordance to the Mott's second argument. So for a parallelly aligned magnetic layer, the upspin, if you see this parallelly aligned magnet, this is going to become more clear if you look into the figure. If you have a parallelly aligned magnetic layer, then these upspin electrons are going to pass very smoothly, but the downspin ones are going to be scattered. This is because of the assumption that the scattering is strong for electrons with spin anti-parallel to the magnetization direction. So according to this, the upspin one passes smoothly, whereas in case of downspin, there is a lot of scattering. Because their spin is parallel to the magnetization of the layers. This is for the parallelly aligned magnetic layers. But the downspin electrons are scattered strongly within ferromagnetic layers because the spin is anti-parallel to the magnetization layer. So now let's see what is happening when we have R parallel. So you are having now these two channels. One is the up one is the down one. So in one case, it is very smooth. In the other case, there is a lot of scattering. Whereas if you have an anti-parallel arrangement, then what is happening? Since conduction occurs in parallel for the two spin channels, the total resistivity of the multilayer is determined mainly by the highly conductive upspin electrons and appears to be low. So the total resistivity in this case, when you are having a parallel, when the conduction occurs in parallel for the two spin channels, the total resistivity is determined mainly by this high conductive, this upspin electrons, because it is moving very fast, it's not getting scattered. So the resistivity is dependent on that, and so it will be highly conductive because the resistance is less. But for the anti-parallel aligned magnetic multi-layer, both the upspin and the downspin electrons, they are scattered strongly within one of the ferromagnetic layers, because within one of the layers, the spin is anti-parallel to the magnetization direction. Therefore, in this case, the total resistivity in the multi-layer is very high. So in this particular case, the resistance is high. In this particular case, the resistance is low. So as you can see, what we said, that because of this arrangement, you find the resistance changing. It is because of how the upspin and the downspin electrons are allowing, the movement of the upspin and the downspin electrons, how it is getting affected with the magnetic field. That is what determines your change in resistance. So if you see the different types of GMR, so you can have in this A figure is showing you materials which is basically alternately ferromagnetic, non-magnetic, ferromagnetic, non-magnetic. So in this magnetic multilayer, we are having ferromagnetic layers which are separated by non-magnetic spacer layers. So due to the antiferromagnetic interlayer exchange coupling, they are aligned antiparallel at zero magnetic field. So as you can see over here, the dashed arrows as well as the solid arrows. So at the saturation field, the magnetic moments are aligned parallel. So what happens when there is no field? In that case, what you have is the antiferromagnetic interlayer exchange coupling. So what you have is those dashed arrows which you see, they are kind of opposing each other. Whereas the moment you apply a magnetic field, then immediately you find only the solid arrows. So this entire ferromagnetic layer, you will find that the magnetization is aligned in one particular direction. So that is the way basically in this particular case, the resistance change is happening. In the pseudo spin bulb, this is a pseudo spin bulb, what you have is a ferromagnetic material which is hard. You have a non-magnetic layer, and then you have a ferromagnetic layer which is made up of a soft material. So this is combining hard and soft magnetic layers. So what is happening, as I mentioned, that the hard and soft magnetic material, they have different coercivities. And so due to this different coercivity, the switching of the ferromagnetic layers, they will occur at different magnetic fields, providing a change in the relative orientation of the magnetization, and this will lead to a change in the resistance. So this is basically a pseudo spin bulb. Now what you have is a spin bulb, a normal spin bulb, that is C. Here you are having a top ferromagnetic layer which is having an antiferromagnetic layer kind of pinned to it. You are pinning an antiferromagnetic layer on top of this ferromagnetic. So the bottom ferromagnetic layer, as you can see, this is free to rotate by the applied magnetic field. So because this is free to rotate and that is pinned, so again due to this change, you will find again a change in the resistivity, and this is also going to give rise to GM. That is giant magnetoresistance. And then there can be, this is the most common one. These are granular thin films. What you have is these kind of magnetic precipitates which are kind of embedded in the non-magnetic metallic material. This is a non-magnetic metallic matrix in which you have these magnetic precipitates which are embedded. So what happens when there is no field? Then as you can see, they are kind of aligned in any direction. The moment you apply a field, they become oriented in a certain direction, and the moment this orientation happens, then you find that resistance changing. It will allow the upspins to pass or the downspins not to pass, and at the end of the day, what you find is basically a change in the resistance, and this gives rise to a GMR effect. So what is this application of this giant magnetoresistance? So what kind of application these GMR materials are used? So this is the largest technological application, please remember, is in the data storage industry. In data storage industry, GMR is used massively. So the GMR read head sensor in a hard disk is built using something which is known as a spin bulb. As I said, in the spin bulb, if you remember, you have an antiferromagnetic layer which is pinned to the ferromagnetic layer. Then you have a non-magnetic layer followed by a ferromagnetic. And it is this ferromagnetic layer which is free to move when you're applying a magnetic field. So now spin bulb resistance demonstrates a steep change in a small field range which is very close to H is equal to 0, where the external field, magnetic field which we apply is almost equal to 0. So as the magnetic bits on the hard drive, they pass under this read head, the magnetic alignment of the sensing layer of the spin bulb changes, and this results in a resistance change. As you can see over here. So this is the head. And whenever the magnetic bits on the hard drive, they pass under this read head, the magnetic alignment of the sensing layer in the spin bulb will change because of the associated resistance change. So as the read head passes over the disk, the free layer shifts its magnetic orientation to match that of the bit. So sometimes the direction of the free layer's magnetic field is going to be aligned with the field of the pinned layer, which never changes, and sometimes it is going to be opposite. So when they are aligned, most of the electrons will share the same up or down spin. As some of these electrons will pass through the layers in the form of current, then there is going to be minimum scattering. The low resistance means that a current is going to be detected, and the computer is going to give you that kind of a reading. So this is how basically the application of GMR works in case of in GMR read head sense. So now when the free layer's magnetic orientation, it will switch opposite to that of the pin layer. Then what is going to happen? There's going to be a much different result. Now the electrons in the two layers, what they are having are opposing spins. So as the current is passing through the magnetized layers, those electrons will scatter in one or the other of them, resulting in a much weaker current and a zero. So what you have is when it is matching one particular magnetic orientation, in that case, if the resistivity is very high, in that particular case, you will have a weaker current, and so it is going to be zero. The other way, what is going to happen? The resistance is going to be low. In that case, the current is going to pass, and if there is a higher current, what you have is something which you know as 1. So you have a 1 and 0 rating, and this is how basically this is achieved using GMR. And since the resistance change is very high in this case, there's a giant magnetoresistance, then the sensitivity of your read head sensor it improves manually. Now coming to the next topic, which is ferroelectrics. So what is ferroelectrics? We have now, so far we talked about ferromagnetism. So regarding the entire magnetism, we learned what is that ferromagnetism is a cooperative phenomena. In this particular case, you have different domains which have different kinds of magnetization. And when you are applying an external magnetic field, then they are kind of aligned to each other and they give rise to a large amount of magnetization. And that large amount of magnetization is basically found in materials which we have named as ferromagnets. So ferromagnetism is one particular concept. Now this same concept, it was also discovered in case of certain materials which have spontaneous electric polarization. In magnets, we found magnetic polarization, but in certain materials, we find the spontaneous electric polarization, which can be reversed by the application of an external electric field. So how we define ferroelectricity is it is a characteristic of certain materials that have a spontaneous electric polarization, which can be reversed when you are applying an external electric field. So if you apply a small electric field, where it is, it is small enough so that it is not able to switch the domain alignments, then what happens, the material, it behaves as a normal dielectric material. So here your polarization is directly proportional to the electric field. But as you increase that electric field, then what happens, the domain starts flipping. And if it starts flipping, then it increases the polarization. So when all the domains are switched, what happens is basically we have reached the saturation polarization. The polarization is maximum. So now what is going to happen if that particular electric field is removed? So this is exactly what we saw in case of a ferromagnetic material also. So when you increase the electric field, the polarization keeps increasing. Now you remove the field, the polarization doesn't drop directly to zero. So some part of it still stays aligned. So you have something which is known as a remnant polarization. And then if you switch the electric field on the negative direction, you apply more field on the other direction, then gradually this polarization, it comes to zero. And where it attains zero, this is known as the point where basically some kind of coercive force you can see. And then again it moves down and it moves up exactly in the same way which we saw in case of a ferromagnetic material. So the essential feature, please remember, of a ferroelectric is not that it has a spontaneous polarization, but that the spontaneous polarization can be reversed by the application of an electric field. So what happens is that you have a spontaneous polarization, good and fine, but the major thing is that when you are reversing, when you are applying the electric field on the other direction, then the polarization can be reversed. And this can be reversed by the application of the electric field. So now there is a very a very good correlation between crystallography and ferroelectrics. So the crystal classification of a material, it has immediate implications for ferroelectric effects. I'm sure in some previous lecture you must have covered this crystallography things. So there are these 32 different crystal classes, as you have already seen, I think in the initial first 4-5 lectures. There are these different 32 crystal classes. So now 11 of them have a center of symmetry. So this TH, OH, C4H, D4H, D2H, C2H, Ci, S6, D3D, C6H, and D6H. So all of them, they have a center of symmetry. And if they have a center of symmetry, then they cannot support ferroelectricity. So automatically, these particular crystal classes are eliminated. So whenever you have a particular material which belongs to these 11 crystal classes, you can say that these are not going to be your ferroelectric materials. Now from 32, we have eliminated already 11. So now we have 21 left. So out of this, again, this O crystal class belonging to O point group, this also is not ferroelectric. But the remaining 20 classes, they all exhibit a piezoelectric effect. So what's the piezoelectric effect? So there, when you are applying an electric field, there is going to be a change in the stress or in the dimension of the particular material. So this is known as a piezoelectric effect. So now if you look into the thing, this relation between piezo, pyro, and ferroelectric point groups. So you have 32 point groups, out of which 11 are centrosymmetric, so they are anyway crossed out. So these are the centrosymmetric ones. They will not show any kind of ferroelectric or piezoelectric effect. Out of this 21 non-centrosymmetric ones, there is one exception, which is point group 432, or which is also known as O point group. That doesn't show any kind of ferroelectricity. Whereas out of the remaining 20 are piezoelectric. So 10 of them are non-polar. You have to keep them out. Whereas other 10 are polar, and they are known as pyroelectric. So out of this pyroelectric, if they are having reversible polarization, they are ferroelectric, and others, they have non-reversible polarization. So if we see piezoelectric, this is the group among which pyroelectrics is a subgroup, and further then we have what a subgroup which is known as ferroelectric material. So this is the relation between piezo, pyro, and the ferroelectric point groups. Now, perovskite is one of the primary examples. Perovskite material is one of the primary examples of ferroelectric. Perovskite is nothing which is a naturally occurring mineral, and it has the chemical formula calcium titanate, CaTiO3. So this is a prototype for many AbO3 or perovskite material, which are very important in ferroelectrics. And these materials may be envisaged by consideration of a non-polar cubic basic building block. So this is basically the structure. So the A ions are basically occupying the corners of the cube. You have your B sitting right at the center, and you have your 6 oxygen which are octahedrally attached to this cation. So now, below the Curie temperature, obviously because it is, I said it's a ferroelectric material, so there will be one temperature above which it will lose that ferroelectric quality, and that is known as the Curie temperature. So below the Curie temperature, these crystals, they undergo symmetry lowering distortion. So there are, if you consider barium titanate, then there are 3 phase transitions of barium titanate. Barium titanate also a well-known perovskite material. So there are 3 phase transitions of barium titanate in order of decreasing temperature. So at around 120 degrees centigrade, then you have at 5 degrees centigrade, and then you have minus 90 degrees centigrade. So it has these 3 different kind of phase transitions happening where it lowers the symmetry. So the lowest temperature yields rhombohedra, which is distortions across the body diagonal. As you can see over here, this is a distortion against the body diagonal. So there are therefore 8 equivalent distortion diagonals. So this barium titanate, it exists in one of 4 polymorphs depending on your temperature. So from high to low temperature, the crystal symmetries of these four polymorphs are cubic, tetragonal, orthorhombic, and rhombohedral crystal structure. All of these phases exhibit the ferroelectric effect apart from obviously the cubic phase. So tetragonal, orthorhombic, and rhombohedral crystal structure of barium titanate, which you will get by changing the temperature of the system, you will find all of these three exhibiting ferroelectric effect. So now ferroelectric finds a lot of application in RAMs, which are random access memories. So first, let's discuss what is RAM. I'm sure all of you are not on the same page. All of you will not know how exactly a random access material, how it works. So these are random access memories. And what do you mean by random access memory? They have symmetric read and write access time. So non-volatile memories, normally what we are non-volatile memories? So they are traditionally ROM. So these are only read-only memory. So until the advent of the floating gate technology. Basically, non-volatile memories or ROM was there, and till the time the floating gate technology didn't come, they had only been read-only memories. So they had always been volatile memories. So for non-volatile memory, it came into existence since the floating gate technology was kind of developed. So it produces this floating gate technology. It produces electrically erasable memories. So flash or EEPROM. So these are electrically erasable memories. So these products allow for in-system programming. But in this case, what happens? The read and the write access times, they are not similar. So the write access times in this case, they are several orders of magnitude greater than the read access time. Now, in case of a ferroelectric random access memory or FRAM, what you get is a truly non-volatile random access memory because it combines the advantage of a random access memory with a non-volatile memory. So the write advantages over flash and EEPROM and the non-volatility, it makes it very suitable for storing data even in the absence of power. So that is why we are kind of moving into ferroelectric random access memory. So what is a floating gate? As I said that initially it was all volatile memory using ROM. So that was a read-only memory. But then basically we moved into somewhat non-volatile by the development of floating gate basics. So what is a floating gate? So in a typical flash memory, it uses a floating gate to store a bit by the presence or absence of a charge. So if the floating gate is not charged, so this is the floating gate as we say. So if this is not charged, if this floating gate is not charged, then the device will operate almost like a normal MOSFET. So a positive charge in the control gate, it creates a channel in the P substrate that carries a current from the source to the drain. So in this case, if you are having a positive charge in the control gate, as you can see over here, then it will create a channel in the P substrate and that will carry a current from the source to the drain. But however, if the floating gate is now negatively charged, then this charge will now shield the channel region from the control gate and it will prevent the formation of a channel between the source and the drain. And the threshold voltage is the voltage which is applied to the control gate at which the transistor is going to become conductive. So the presence or absence of the charge results in a more positive or negative threshold voltage. So in a flash memory language, programming or putting electrons into the floating gate, it means you're writing a 0 because obviously it is not allowing this particular thing to move because it prevents the formation of a channel between the source and drain. And erasing or removing the charge from the floating gate, it means resetting the flash memory contents to 1. So a programmed cell stores a logic 0, whereas an erased cell will store a logic 1. So this is the kind of the basic of a floating gate. Now you have to remember the floating gate is completely surrounded by an isolation layer. So this enables the floating gate transistors to be used as non-volatile memory. But it also imposes the need to find ways to charge and discharge it. So the floating gate technology, it is isolated. So definitely that is the reason why you do have a non-volatile memory. But the problem is that you need to find ways to charge and discharge it because it is now wrapped in an isolation loop. So now how the ferroelectric RAM is developing on this particular thing, and it is making it even better. So now if you remember the FRAM, the ferroelectric RAM is built on obviously ferroelectric technology. So it contains a ferroelectric film of lead zirconate titanate, which is commonly referred to as PZT film. So the atoms in the PZT change polarity in an electric field, thereby producing a power efficient binary switch. However, the most important aspect of PZT is that it is not affected by the power disruption. This is very important. It is not affected by power disruption, and that is why it is a very reliable non-volatile memory. So as you look into this particular PZT material, in a down polarization, this cation is moving down, up polarization, the cation is moving. So the cation in the center has two equal and stable low energy states, and this states it determines the position of the cation. So when you apply an electric field across the crystal, it causes the low energy state or position to be aligned to the direction of the field. Conversely, higher energy state will be in the opposite position. So the applied field will therefore cause the cation to move from the higher energy state to the low energy state. And this produces energy in the form of a charge, which is referred to as the switch charge. So you have something which is known as the switch charge. So therefore, the alternating electric field across the crystal will cause the cation to move from the top of the crystal to the bottom and back again. So there is a kind of binary switch movement happening, a switch charge alteration is happening because of the application of this electric field. So the basic storage element of in this type of FRAMs is the ferroelectric capacitor. So the capacitor, it can be now polarized up and down by applying the electric field. So if the ferroelectric capacitor is not switched when an electric field is applied, so then it is behaving as a normal linear capacitor. But if it is switched, then what happens? Then an additional charge is induced, as I mentioned in the previous slide. So therefore, the capacitance must increase. So the ferroelectric capacitor, it generally how the attachment looks is, it is combined with an access transistor, then it has a bit line, it has a plate line, and it forms a memory cell. So the write operation, it's actually very similar to the read operation. The circuit applies an electric field in the desired direction across the ferroelectric capacitor. So you have to understand how basically the FRAM operates. If it is not switched, then it will behave as a normal linear capacitor. But the moment it is switched when the electric field is applied, then an additional charge is induced and the capacitance increases. So with this, basically you are having two different states formed. And because of this, you have that kind of a random access memory. And the best part is that in this particular case, even when the power is switched off, it doesn't change the state. So it is able to store. So that memory stays stored. So it is combining the best of a random access memory as well as non-volatile memory. Now, we have discussed magnetic effects. We have discussed ferroelectric effects, ferromagnetic effects, ferroelectric effects. So now we'll discuss something which is known as the magnetoelectric effect. So the magnetoelectric effect is characterized. So here what happens? You are varying the electric polarization in response to an electric external magnetic field. So far what we have seen is we are changing the external magnetic field and the magnetic polarization field. We are applying an electric field and the electric polarization field. But now, as this particular topic is telling us, it is magnetoelectric effect. So in this case, what is happening? If you are applying an external magnetic field, there is a change in the electric polarization, or an induced magnetization happens when you are applying an external electric. So this polarization, the electric polarization, is a function of your electric field as well as something which is known as when you're applying an external magnetic field. Similarly, your magnetic, the entire magnetic polarization is again dependent not only on the external magnetic field, but it is also dependent on the external electric field. So here, now, if we look into this, what are the definitions? This chi E is basically the electric susceptibility tensor. Chi M is the magnetic susceptibility tensor. Whereas chi Ij EM, this is again equal to chi MEJI. And this is delta square phi by delta EI and delta Hj, which is mixed magnetoelectric susceptibility tensor. So here delta EM is the chi EM is nothing but delta P by delta H, which is change in your electric polarization due to a change in the externally applied magnetic field, whereas chi ME is the change in the magnetization due to a change in the applied electric field. And this phi over here is the thermodynamic potential. So the following equation in the vicinity of the phase transition point is in force. So this chi EM is chi EM, which is T minus T to the power of minus half. So in a phase transition point, this is how this particular value is going to look, or this mixed magnetoelectric susceptibility tensor is going to behave. So what is this exactly the magnitude? That was the mathematical expression. So what do we actually mean by it? So it's a phenomena of inducing magnetic or electric polarization by applying an external electric or magnetic field and vice versa. So the effect can be linear or it can be non-linear with respect to the external field. And in general, this effect, it depends on temperature. And the effect is generally expressed in the following form, as you can see over here, Pi and Mi. This is how it is expressed. So if you look into this particular slide, what you have is when you are having an electric field applied and magnetization changes, or you have a magnetic field applied and the polarization changes, then what you have is known as a magnetoelectric effect, or ME. Similarly, there can be two different types of magnetoelectric effect. One can be direct effect, and the other can be a converse ME effect. So multiferroids are defined. Now, when then you can have different types of combinations are also possible. In some particular case over here, as you can see, this vibration, this is nothing but piezo. So if you are having a magnetic material and you're applying a magnetic field and it is kind of changing, it's producing a kind of a stress in the material, or it is changing the dimension of the material, then you have something which is known as a magneto-piezoelectric effect. So these two different kinds of things, if you're combining with applying one particular field, the other polarization gets affected. This is known as a magnetoelectric effect. When you're applying an electric field and magnetization changes, or you're applying a magnetic field and the electrical polarization changes. So now, on the basis of this, we have a very, very radical kind of material. These are known as multiferroids. So multiferroid materials is a very, very hot field of research. These are defined as materials that exhibit more than one of the primary ferroic order parameters in the same phase and leads to the formation of switchable domains. So you have ferromagnetism, you have ferroelectricity, you also have something which is known as ferroelasticity, which is nothing but spontaneous strain. So if you have ferroelectric combined with ferroelastic, then you say you have a piezoelectric and electrostatic coupling. If you have a ferromagnetic with ferroelastic, you say you have a piezomagnetic with magnetomechanical coupling. Whereas if you have a ferromagnetic with a ferroelectric material, you have magnetostrictive and piezoelectric coupling. So now let's look into this different, it's a kind of a set diagram. So what happens in ferroelectrics? What you see is you are changing the electric field, you find the change in the electric polarization. In case of magnetic materials, you have a change in the magnetic field with a change in the magnetic polarization. In multiferroids, they form a very special type of materials where if you change the electric field, you find a change in the magnetic polarization, or you change the magnetic field, you find a change in the electric polarization. So you see EH here and PM there. This is nothing but a multiferroic material. This is in the cusp of basically both ferroelectric as well as ferromagnetic material. So the same thing is shown over here in this particular diagram. You have magnetically polarizable material, out of which ferromagnetics forms a small subsection. You have electrically polarizable materials, of which ferroelectric forms a small subsection. And again, in the intersection of this ferromagnetic and ferroelectric, what you have is multiferroid. Whereas if you are having something which is both electrically polarizable and magnetically polarizable, or it can be both ferromagnetic and ferroelectric. In that case, what you have is a magnetoelectric medium. So you have multiferroids, you have magnetoelectrics. So these are all these examples are of multiferroid materials. So a ferroic material, as I said, is basically a material which exhibits either ferroelectric or ferromagnetic or ferroelastic ordering, a feature typically demonstrated by the presence of a well-defined hysteresis loop when the material is switched either electrically, magnetically, or mechanically. So this is the definition of a ferroic material. So what are multiferroids? From ferroic, the definition of multiferroic can be easily obtained. So multiferroics are materials which possess more than one type of primary ferroic ordering in a single phase. So this is the same same diagram which was shown in the previous slide. So the multiferroic materials, what are the examples of multiferroic materials? They can be rare earth manganites or ferrites or transition metal perovskite oxides. The examples are TbMnO3, TbMn2O5, holmium manganates like HOMn2O5, lutetium ferrites like LuFe2O4. This is a very important material, bismuth ferrite BiFeO3, bismuth manganate BiMnO3, and yttrium manganate YMnO3. And some non-oxide materials are also multiferroids, such as barium nickel fluoride, and the spinel chalcogenides like ZnCr2Se4. So these are the various classes, various types of multiferroic materials which are being pursued very rigorously in multiferroic research. So, as I said, what are multiferroic magnetoelectric materials? So, materials which have the coexistence of long-range ferroic orders, and there is a very strong coupling between pertinent order parameters. So if you have a magnetic material, and along with it you have a piezoelectric material, then the composite of this, it will definitely, if you have a composite of these kind of materials where magnetic material is mixed with a piezoelectric material, it will lead to additional control to input and store data. So the applications can be vast. So you can have application in sensors, in multi-state memories, as actuators, device applications, as well as biomedical field, etc. So bismuth ferrite, as I said, is a single phase multiferroid. It exhibits magnetoelectric coupling at room temperature. That is why it is a hugely researched material. So now in multiferroids, as I said, because of that phase thing, there can be type 1 and type 2 multiferroids. So type 1 are single phase multiferroids in which the magnetic and the electric phase coexist within the same compound, but they have different microscopic origins and they are broadly independent of each other. So you have in the same phase, you do have magnetic and electric phase, but the origin of the magnetic and electric phase is different. So magnetic phase is independent of the ferroelectric phase, though they are the magnetic, So they are kind of independent of each other, though the material is in single phase. But in type 2, these are also single phase multiferroids, but in which the ferroelectric order is induced by magnetism, which in turn suggests a very strong magnetoelectric coupling. So in this case, what happens is you have a magnetic arrangement which induces a ferroelectric order. So in this case, the microscopic origin of your ferroic order is interdependent on each other. And so these type of materials are known as type 2 multiferroids. So if you have different kinds of interactions are there, you can have spin charge, you can have spin lattice, and you can have spin orbit. So this is basically your magnetization, and this is your charge polarization, electric polarization. So this coupling can be of different types. You can have the spin orbit, you can have spin lattice, or you can have spin charge coupling. So what are the mechanisms which support multiferrocity? So ferroelectricity is driven by electronic lone pairs. It can be driven by presence of electronic lone pairs. It can have geometric effects, which is giving rise to ferroelectricity, or charge order. So in case of type 1, what happens, as I said, is the magnetic and the ferroelectric order, they occur independently. So one of the most prime example is the lone pair mechanism, and this lone pair mechanism, the biggest example is BiFeO3. So based on the spatial asymmetry created by the anisotropic distribution of unbonded valence electrons around the host ions. So the lone pair mechanism is based on the spatial asymmetry which is created by the anisotropic distribution of unbonded valence electrons around the host ion. So here the ferroelectricity originates from two bismuth 3 plus electrons that shift away from the bismuth 3 plus ion, as you can see over here, the bismuth 3 plus ion, and towards the FeO6 octahedron, giving rise to spontaneous polarization P along the 111 direction. This is a 111 direction and it gives rise to a spontaneous polarization along that direction. The lone pair over here is visualized by the isosurface or the red one of the electron localization function of ferroelectric Bi project. So what essentially this means is there is a spontaneous polarization due to the arrangement of those two lone pair electrons on bismuth. Bismuth has those NS2 electrons, 6s2 ones, which are not taking part in bonding. These stay as lone pairs, and how they are oriented in the crystal, that actually gives rise to a spontaneous polarization. So BiFeO3 shows spontaneous polarization of 100 microcoulomb per centimeter square below the Curie temperature. The TC is around 1103 Kelvin, and a long range periodic antiferromagnetic structure rises below the mean temperature, which is 643 Kelvin. Please remember that among the lone pair systems, BiFeO3 is the only room temperature single phase multiferric nucleus. This is very important. It's a room temperature one. Most other single phase materials, they do not show multiferrism at room temperature. So now the next mechanism, as I said, was the geometric effect. So let's look into geometric effect. The space filling effect and geometric constraint. It can also cause structural instabilities in materials. And if such steric effects rather than the bond chemistry leads to ionic shifts, it will result in the formation of a polar state, and the term geometric ferroelectricity is used. So in this case, let's take the example of hexagonal RMnO3. It emerges from a tilt and deformation of the MnO5 bipyramids. So in this case, what happens is you are having, this kind of a steric crowding. So in this case, the polarization of this particular ion happens. So in FME3, the unit cell tripling drives the emergence of a ferroelectric order at the Curie temperature, which is 1200 Kelvin, with a polarization of 5.6 microcoulomb per centimeter square, and which is followed by a magnetic ordering at 120 K. So in this case, it is basically the steric crowding effect which is giving rise to the polarization. So this is a geometric ferroelectricity. The other, as I said, the last one was the charge order. So valence electrons, it can be distributed non-uniformly around the host ions in a crystal lattice, and it forms a periodic superstructure. So charge ordering in such materials like LuFe2O3, it creates alternating layers of Fe2 plus and Fe3 plus in ratios of 2:1 or 1:2. So this creates spontaneous polarization between the two layers, which is either oriented parallelly to the applied. So this is how basically ferroelectricity is supported using charge ordering. Because in this case, you are forming a superlattice with an alternating sequence of Fe2 plus and Fe3 plus ions. Now coming to type 2. Type 2 is also single phase multiferroids, but in this case, the mechanism is spin driven. Please remember that magnetic order, it can break the inversion symmetry. The interaction of spins and charges may transfer the non-centrosymmetry from the magnetic to the electric lattice, driving the formation of a polar state. So these magnetically induced so-called improper ferroelectric materials, they represent the ultimate shift away from displaced ferroelectrics, in which magnetic ordering is inhibited, towards materials in which electric polarization is induced by the magnetic ordering. So here what happens is your magnetic order is breaking the inversion symmetry. Your spin and charge of this particular material, they are interacting and they transfer non-centrosymmetry from the magnetic to the electric lattice. And because the non-centrosymmetry is now occurring in the electric lattice, what you find is the formation of a polar state. So these are spin-driven mechanisms. So there are a few examples. So, few types of spin-driven mechanism. The primary among them is the inverse DM mechanism, we say, which is basically, in this case, what happens is you have an acentric spin structure which drives the non-centrosymmetric displacement of charges. And in this case, it is the spin-orbit coupling which is crucial for this inverse DM interaction. This is known as the inverse Zyloshinsky-Moria interaction. So in this case, what is happening? Polar displacement in this particular case is induced by antisymmetric spin exchange interactions. Like in orthorhombic RMNO3, the polarization vector is P, which is directly proportional to Eij cross product of Si and Sj. Here Eij is what? It is the unit vector connecting the neighboring spins, and Si and Sj are the spins at the neighboring side. So you have Si and you have Sj, and the cross vector of it along with the cross vector of cross with the unit vector, it is going to give you something which is known as a inverse DM interaction, and due to which you find the polarization changing. So you have the spin states, these are interacting with each other, and this ultimately is giving rise to this polarization. So you have a down polarization in this case, and you have an up polarization in this particular case. And this is happening because of the spin interaction. So here spin is pointed in one direction. When it moves into the other direction, it is kind of inducing this particular polarization. So it is a one-to-one correlation between the antiferromagnetic order and the electric polarization. So this is one type of spin mechanism which is giving rise to your type 2 multiferroids. The other is a Heisenberg-like exchange friction, and this is an eccentric displacement of charges which is derived from the optimization of the symmetric spin product Si dot Sj. So ferroelectricity is generated by this kind of displacement, and this was first observed in materials like TbMn2O5. So what this essentially means? So there is a dominance of the non-relativistic symmetry exchange over the relativistic antisymmetric mechanism. So here Si dot Sj, this is going to be much greater than that of this interaction is going to be much greater than that of the cross product of Si and Sj. And so there is an order of magnitude increase in the polarization when a cycloidal order, which is parametrized by this Si cross Sj, is transformed into a collinear antiferromagnetic order. And this is given by Si dot Sj. So these are the mathematical expression, but please understand the physical meaning. So if you have something like TbMnO3, it has a cycloidal order. When it is transforming into an antiferromagnetic order, which under pressure, if this crystal structure is changing, in this case, this is what it is going to lead to is because of this change in the structure from the cycloidal order to the antiferromagnetic order, you will find the change in the polarization happening. So because of this change in the polarization which is happening due to the change in the magnetic, this is again a multiferroid. So it's a single phase multiferroid, but this is a spin driven mechanism. But this particular type of exchange is known as a Heisenberg-like exchange friction. The last one is the spin-dependent PD hybridization. In this case, the spin-driven modulations of the chemical bond between magnetic 3d orbitals in this case and the ligand 2p orbitals, they yield a spontaneous polarization along the bond direction. So you can see here P is equal to 0, whereas the moment this bond forms, there is a spontaneous alignment, a spontaneous polarization along the bond direction as is shown over here. And this is generally observed in materials which are Delafossite kind of material, that is UFeO2. And again, you see that because of the spin-driven modulation of a chemical bond, what you see is an electric polarization happening. So it is a spin-driven polarization, electric polarization. And so this is again an example of type 2 multiferroids. So now let's compare the different mechanisms. So if you have lone pair, if you look into the polarization and the different types of the interaction which is giving rise to that kind of polarization, you find the lone pair mechanism, that is the one which we saw in BiFeO3. I mean, this gives the maximum polarization. Whereas when you look into charge ordering or when you look into geometric ferroelectricity, the geometric ferroelectricity basically shows much less polarization compared to the lone pair polarization. And that is why in type 1 multiferroids, BiFeO3 is the most researched material. So this displays the BiFeO3 displays the largest spontaneous polarization, In the relaxed form, the polarization is 100 microcoulomb per centimeter square, whereas in the strained form, it is 150 μc per centimeter square. And among the spin-driven ones, say look into the spin-driven mechanisms, they are the type 2 ones. Symmetric Heisenberg-like exchange friction lead to a larger polarization than the antisymmetric DM exchange. So this is reflected in the orthorhombic PBMNO3. This experiences a transition from the spiral order to a collinear antiferromagnetic order under pressure. And you see the PS value, it almost increases 1 ohm. So that is why what we find in this particular case is in the spin-driven ferroelectrics, it is the symmetric Heisenberg-like exchange friction which leads to more polarization. So far, the lone pair mechanism has been the most successful in enabling multiferricity with the right characteristics for device applications. But the biggest problem is only BiO3 is the known material to be multiferroic because of this particular mechanism. However, many spin-driven multiferroic materials are being discovered, and looks like many of them can be actually applied at room temperature. So then basically, since it can be driven at room temperature, then only you can think of device applications in this particular material. So we have to look for multiferroics which show the multiferroism at room temperature. So now let's see domains and domain walls in type 1 and type 2 multiferroics. We have already discussed what a domain wall is, domains and domain walls are in case of magnets. So let's see what is the domain and domain wall in type 1 and type 2 multiferroics. So as I said, in type 1 multiferroics, you have separate region where separate origin for magnetic order, and you have a separate origin for the electric order. So the respective domain patterns do not have to coincide, and domain walls, they can either be only magnetic, which is this blue line, or it can be only electric in nature, which is this red line. If the domain patterns are coinciding, if somehow in some region where they are coinciding, in that case, what you will have is a multiferroic domain wall. And this, in this particular case, as you can see, is this orange line over here. And this points to a coupling between the magnetic and electric order, which, however, in this particular material is not required by silicon. But if that kind of coupling is happening, then you have a multiferroic domain. Whereas look into what is happening in case of a type 2 multiferroics. Here, a magnetic order induces electric order. Thus, ferroelectricity emerges jointly with a magnetic phase transition. And so there is an interdependence between the electric and the magnetic field. So all ferroelectric domain walls are also magnetic domain walls. So in case of a type 2 system, all the domain walls are basically multiferroic. So this is the difference. In case of a domain wall for a type 1, you can have a ferromagnetic wall, you can have a ferroelectric wall, or else you might also have a multiferroic wall, in which multiferroic domain wall, where there is a coupling between the magnetic and electric wall. But in a type 2, essentially, it has to be a multiferroic domain. Now, another important type of material which needs to be discussed in multiferroics is composite multiferroics. And composite multiferroics are being developed because of the lack of single-phase multiferroics operating at room temperature. And they also essentially have very weak magnetoelectric coupling. So then it becomes very uninteresting and unattractive for application. So application, what you need is multiferroics which are operating at room temperature, and they also have strong magnetoelectric coupling. So what you do is now you develop magnetoelectric composites. So multiferroic composites are compounds in which electric, magnetic, and piezoelectric order it exists within the material. But unlike single-phase multiferroics, which are homogeneous, and chemically isotropic, the composite ones, obviously, as the name suggests, are characterized by the fact that the order phases are physically separated from each other within the multiferroic composite material. However, the resultant magnetoelectric coupling in these materials can be almost 108 times larger than what you see in a single-phase multiferroic material. So that is why there is a lot of research going on in composite multiferroics. And the condition for strong magnetoelectric effect in composite is that the two individual phases, they should be in equilibrium. Mismatching between the greens should not be present. And the magnitude of the magnetostriction coefficient of the piezo-magnetic or the magnetostrictive phase and the magnitude of the piezoelectric coefficient of the piezoelectric phase must be high. The accumulated charge, it must not leak through the piezo-magnetic or the magnetostrictive phase. And the strategy of pooling of the composites must be determined. So these are the different conditions which needs to be fulfilled to have a very strong magnetoelectric effect in composite. So when you're combining two materials, you have to see, whether it is satisfying all these different parameters. So as I said, there are a lot of application of ferroics. They are used in ferroic means, as I said, it can be magnetic, it can be electric, it can be piezoelectric, it can be elastic, ferroelastic. So in transformers, amplifiers, phase shifters, frequency multipliers, displays, wave filters, generators, mechanical shifters, transducers, sensors, memory devices. So there are so many applications of ferroic materials. But when we come to the application of multiferroids, why multiferroids? It can be used as AC/DC magnetic field sensors, highly sensitive sensors, magnetic field sensors. How? See, magnetic sensors, they are devices that can detect without physical contact the creation or variation in magnetic fields in the surrounding environment. And from these changes, they derive information on the on the properties of the magnetic field itself, as well as indirect properties of other entities such as direction, rotation, angle, speed, electric currents, temperatures, and so on and so forth. So magnetic sensors, they are detecting magnetic fields. So what does the a multiferroic kind of a sensing element do? So in this case, if you see for a multi-ferroic material, if you are using as these kind of sensors, this voltage response of the multiferroic sensor, which is V, this is given as alpha H to the power alpha H V into H into T. Well, what is this H? H is the external magnetic field applied. T is the thickness of your ferroelectric layer in case of the laminates. And this magnetoelectric voltage coupling coefficient is given by this alpha HV. So now a linear response is critical requirement in order to operate this thing as a sensor. So coupling measured at intermediate angles between 0 and 180 degree, they show almost a linear variation, as you see over here. It's almost a linear variation. And this indicates the possibility of using the multiferroic sensors for direction detection as well as softness applications also. So by applying a little bit of, electric field, the voltage can change, and if this voltage is changing as a factor of this magnetoelectric voltage coupling coefficient, in that case, you will find a large change in the voltage happening. And that is the reason why these will have a lot of, the sensitivity of these kind of sensors are going to be much, much more. Then you have multiferroic microwave resonators, which can be tuned electrically. So ferromagnetic materials subjected to high frequency excitations, they display ferromagnetic resonance. Ferromagnetic resonance, it occurs when the frequency of the precision of your material, they are precessing, right? That is how the magnetism is happening. Precision, it matches the frequency of the excitation field, and this typically occurs at microwave frequency in case of all the ferrite materials. So radar and communication technologies, they require rapid switching from one operating frequency to another with minimal power. So if you are replacing these kind of ferrite materials with multiferrite bilayer composite, electric field tuning of these kind of ferromagnetic resonance is possible. And the effect of the applied electric field can be viewed as the creation of an internal magnetic field, which is responsible for the shift in the FMR waves. So by using an electric field, you can change the magnetic field. This causes less of a disturbance, and it becomes much faster. That switching becomes much faster. And so obviously this can be used as microwave resonators, which can be tuned electrically. And a very important application which can happen if you can have this room temperature multiferroic materials is in multiferroic magnetic recording read heads. So in this case, what is happening is the sensor stack is basically a planar structure that incorporates a tri-layer ferromagnet, ferroelectric ferromagnet, multiferroic composite structure. So this operates as an alternating magnetic field detector via a magnetically induced magnetoelectric effect. So essentially, what does this mean? There's too much of technical jargon over here, but essentially what it means is, as the head moves along the magnetic recording track, the field from the recorded bit, it provides an AC excitation field to the multiferroic readout sensor. In order to induce a strain-mediated magnetoelectric effect, a DC magnetic field bias is also required. And the best way to bias the multiferroic composite sensor is via a self-biasing mechanism using an exchange bias effect between the ferromagnetic layer and the antiferromagnetic layers. So once this happens, what is the advantage? Definitely you have a reduced power consumption. You have improved thermal performance. As you remember, the multiferroic reader is capacitive rather than it is resistive. So higher operation frequency and thinner reader containing maximum maybe 7 layers, they allow magnetic recording densities of 1 terabyte per inch square and beyond. So there is a huge capacity increase if you are able to use this kind of multiferroic magnetic recording heads. And another very important application, as I said, we now using ferroelectric RAMs. Instead of that, if you can use a multiferroic random access memory, then two binary states could be encoded by the ferroelectric polarization state, and by integrating the multiferroic within a magnetoresistive multilayer, two additional binary states could be encoded in the resistance state of the multilayer stack. So what you have is strain-mediated magnetoelectric coupling in multiferroics, which is utilized to achieve the magnetization rotation of the free layer. So this multiferroic RAM could operate as an all-electric read-write 4-state memory RAM, offering less power consumption, more memory density, and non-volatility simultaneously. So instead of a 2-state memory, using a multiferroic random access memory, you can have a 4-state memory. It will have much less power consumption, very high memory density, and also non-volatility. So with this, we come to an end for your application in magnetic materials. If you have any questions, you can ask me right now, and I will be answering them. If not, then you can always email me. My email is given in the first slide. So you can email your queries to me and try and answer them. So if there are no questions, then we end the class now. Good evening to all the participants, and to those who will be logging in later. A very good day to you. Thank you.